Every single time you send an email, stream a movie, or jump into an online game, there's this invisible manager working tirelessly behind the scenes, just making sure everything runs smoothly. It's definitely not the flashy part of the internet, but honestly, without it, our digital lives would just be a complete chaotic mess. So today, let's dive into this unsung hero, the transport layer. In this explainer, we're going to break down 4 critical problems that the transport layer solves for us every single day. We'll start with how data finds the right application on your computer. Then we'll compare the 2 main delivery services of the internet. After that, we'll see how it prevents digital traffic jams. And finally, we'll explore how it creates express lanes for the data that matters most. All right, first up, let's talk about solving what you could call the final mile delivery problem. So the network layer, using an IP address, is fantastic at getting a package of data to the right computer. But once it arrives at the front door, a whole new challenge begins. And this is exactly where the transport layer shines. See, its job isn't just getting data to a destination computer. That's called source-to-destination delivery. Its real mission is what we call process-to-process delivery. That means getting the data to the specific application or process that's actually waiting for it. I mean, think about it. Your web browser, your email client, your Doom call, they're all different processes running on the very same machine. Here's a great way to picture it. Imagine your computer is a giant, busy office building. An IP address is like the street address. It gets the mail carrier to the front door, no problem. But how does a specific letter find its way to Sarah in accounting on the 15th floor instead of ending up with Mark in marketing down on the 3rd, right? Without some kind of internal mail system, it would just be total chaos. The solution is actually brilliantly simple: port numbers. The transport layer assigns a unique port number. Think of it as a digital office or cubicle number to every active application. Then it just stamps that number onto the data packet's header. So when the data arrives, the transport layer just reads that port number and boom, delivers the packet directly to the right application, making sure the entire message gets to the right process. Okay, so now we know where the data is going inside the computer. But the next big question is, how are we going to send it? The transport layer has 2 main delivery services, 2 really famous protocols with completely different ways of doing things: TCP and UDP. Okay, think of TCP as your certified sign-forward courier service. It's connection-oriented, which means it calls ahead with a 3-way handshake to establish a formal connection before sending a single thing. It absolutely guarantees every packet arrives and in the right order. It's super reliable, but all that tracking makes it a little bit slower. UDP, on the other hand, that's like just dropping a letter in the standard mailbox. It's connectionless, it just stamps an address on the packet and sends it off. It's way faster, what we call a best effort delivery, but there are 0 guarantees. Some packets might get lost or show up out of order. And this really gets to the heart of TCP's promise: guaranteed, error-free delivery. And for some things, this level of reliability is completely non-negotiable. I mean, you can't have your email arriving with missing words or a critical file transfer getting corrupted halfway through, right? TCP's reliability is the absolute bedrock for these kinds of applications. So the key here is choosing the right tool for the job. For things like email, file transfers, and loading web pages, you have to use TCP because every single bit has to be perfect. But for real-time stuff like video streaming or online gaming, you go with UDP. And why is that? Because speed is everything. If a single frame of video drops, it's so much better to just skip it and keep the stream moving smoothly than to halt the entire thing just to re-request that one lost piece of data. Here, timeliness totally beats perfection. All right, let's move on to our next big problem. So we've got our data, we've picked our delivery service, but what happens when millions of us are all trying to send data at the exact same time? Well, you get the internet's version of a good old-fashioned traffic jam. Network congestion is, well, exactly what it sounds like. Too many data packets are trying to squeeze through the same network path all at once, way more than the network's capacity can handle. And just like on a highway, the result is slowdowns, drop packets, which are kind of like digital fender benders, and just a really frustratingly slow experience for everybody involved. And here's the problem in a nutshell. As you can see, the amount of data we're trying to send is way more than the network can actually handle. That extra traffic doesn't just, wait politely in line. It creates a digital logjam, causing packets to get dropped and everything to grind to a halt. So how does the transport layer deal with this? It doesn't just blindly keep sending data into the middle of all this chaos. Nope, It uses a really sophisticated set of rules for the road, which we call congestion control, and this is primarily a feature within TCP. The goals here are both proactive and reactive, which is pretty clever. Congestion control tries to prevent jams before they even start by carefully managing the flow of data. It controls how much data is sent out at once. But if packets do get lost or corrupted, which is a sure sign of congestion, it detects this, slows itself down, and retransmits the missing pieces, helping the whole network recover. And that brings us to our final challenge, and it's maybe the most modern one. In a world full of digital traffic jams, what if some of that traffic is just more important than other traffic? This is where we get into the idea of creating express lanes for our data. This whole concept is called quality of service, or QoS. Its entire job is to manage traffic by prioritizing certain data streams over others. You can think of it just like the HOV lane on a highway. It doesn't add more lanes to the road, but it makes sure that the time-sensitive traffic, like your video conference or an emergency call, gets through without getting stuck behind someone's massive non-urgent file download. Now, there are two main ways networks handle this. First, there's integrated services, which is the reservation model. Here, an application can literally reserve a specific amount of bandwidth, almost like booking a private, dedicated lane on the highway just for your trip. The second, and more common way, is differentiated services, the priority model. Here, packets are simply marked with a priority level, so routers know to handle the high-priority packets first, just like letting an ambulance use a special lane to cut through rush hour traffic. And the number one goal of all of this? Timeliness. QoS exists to fight latency and jitter, that annoying, uneven delay in when packets arrive, for all those applications where real-time performance is absolutely critical. It's the magic that lets your video call stay smooth, even when the network is getting slammed. And don't think for a second this is just for the huge internet backbone. QoS is incredibly important right inside your own home or office. A properly configured switch network can use QoS to make sure your important work call doesn't freeze and die just because your roommate decides to download a 100-gigabyte game in the next room. So, let's do a quick recap of our journey. The transport layer uses port numbers to get data to the correct application. It gives us two main choices: the super reliable TCP for accuracy and the speedy UDP for real-time apps. It acts as the internet's traffic cop with congestion control, and it creates express lanes for our most important data using quality of service. It's basically the traffic cop, the mail sorter, and the logistics manager for your entire internet connection. And all this leaves us with a pretty fascinating question for the future. As our digital world just explodes with data, everything from our cars to our coffee makers is coming online, the need to prioritize is becoming more critical than ever. So who decides? Who gets to decide which information gets the express lane and which information gets left behind in the slow lane? That is a huge question that the engineers of tomorrow are going to have to answer.